Today I don't have a bunch of slides, but as I had mentioned in Thursday's class, I was going to jump off of some of the concepts that we discussed in the slides earlier and actually start to do some examples using Yarra to analysis. So one of the examples that I'm pulling in here, and I have this stuff published on the course site, so you can go to this link, which I also sent out a notification to everyone about. I actually pulled down two encryption algorithms that are described in kind of English or math language here. So I'm going to zoom out again. So these are two common encryption algorithms. The reason I bring these up is because encryption algorithms tend to be the type of thing that oftentimes will be used to try and conceal transmission. They very frequently have very compartmentalizable pieces of code within them, and also oftentimes if you are analyzing x86 code or C, something that was compiled from C or C++ or something like that, a lot of times you'll find an implementation of any one of the publicly known encryption algorithms out there, and sometimes you'll even run into cases where it'll be a derivation of one of them. But I picked these mainly because there's a lot of documentation about them. You can look at the documentation to kind of figure out what the code's doing. From the perspective of what we're going to do today, I'm not going to focus so much on how the algorithms themselves work, but instead I'm going to focus on the traits within the implementations of these algorithms that might yield identifiable characteristics. So basically things that we can match on using Yarra signatures. So the reason I picked these is because both of them, of a lot of the different encryption algorithms I could pull, both of these have really small, concise implementations that are available on Wikipedia. There's a number of others like RC4 and others that might have a much more verbose implementation. So I felt these are really good ones to kind of do in-class exercise with. So I've got it all linked here, and I'll zoom this in for those in class. I've got it all linked here. So the way I did it is I actually pulled the code that was on the Wikipedia pages, and the number one example that's up here, so you notice for each one of the algorithms there's actually two different examples. The first one is literally copy-pasting the code. The second ones are actually me going into the C code and making some very trivial modifications to it. So, and then finally you'll notice I have a huge dump of items here. So one of the other things, as I had mentioned before, that you'll tend to deal with is malware analysis generates large number of analysis artifacts. So in this case, we end up having, these algorithms can be compiled for 32-bit and 64-bit execution. So there's already two more versions of each, two implementations of these. So now we're up to 4. And then from that, I ended up basically taking the object file dump of each of them. So the normal object file that can be compiled into a C program or linked into a C program, the disassembly for it, which is listed right here. And let me just double check something. I want to make sure that. Okay, it looks like everything. Okay, cool. I just want to double check that the audio was working. So each one of these, I have the disassembly. So I used the OBJ dump tool that we demonstrated in the last one to disassemble each version, and then that's dumped here. And then I also generated a Hex Dump Summary. So let me see if that's not going to show anything. And I guess that, okay, that's weird. Well, I can fix that. I'll have to fix that. I have them right here, so I will do this. So I basically have them all listed right here. I'm going to bring up the, I don't have it, so I'm going to bring up So I'm going to bring up all 4 of them. So, and just to kind of, I'm a little bit off center with that, but there we go. And just to kind of give you a little bit of a kind of like baseline here is what I will end up doing is I'll show you kind of the changes that have been made. So the reason I'll show you these is they end up being like non-functional code changes, but they do end up having an impact on the compiled code, even though they seem like they shouldn't. So the first one, what you'll notice is that for those of you who aren't aware, encryption algorithms generally end up having these kind of very tight loops in them because you end up working across blocks of data or something like that. So streams of data or blocks of data, and you end up trying to basically intermix, say, all parts of the data with other parts of the data in order to try and create something that looks like a random, unpredictable distribution. So the goal is that when you have the ciphertext, you don't have any way of predicting based on any bit in the ciphertext what any bit in the original product was. So in a nutshell, it's a very hard problem to reverse. What this ends up doing, or I should say how this ends up typically being implemented, is you end up having multiple obfuscation rounds of sorts that end up performing a core encryption routine multiple times, usually attempting to mix all the data with all the other data, or all of the data with a key space of some sort. So in this case, we're trying to do it with, I believe, a key space. And what you'll see is that they break the key, which is this k value right here. They break it up into 4 pieces, so 4 chunks, and then they perform some sort of long, multiple parameter mathematical operation that includes, parentheticals. So at its core, it really ends up being 3 values: A right here, B right here, and then C right here. So it ends up being 3 parameters that are XORed with one another at its core. It does that twice, and then it generates 2 pieces, basically, that then it's returning back, which end up being the encrypted version, right? It's not too difficult. What people have found is if you implement it like this in C, the way I've got it right here, so basically a not very human readable single line multi-parameter mathematical expression, then you end up having a pretty efficient, or I should say you end up having the most efficient compiled result. The other thing that's interesting about this one is that they have a encryption routine and a decryption routine. So that's not always the case. Sometimes on some of them where they have a perfectly symmetric, it's called like perfectly symmetric encryption algorithm, a lot of times you can run the encryption algorithm once, you get the encrypted text, and then if you rerun the encrypted text through the encryption routine again, then you get the decrypted text. You basically have this cycle where it's, performing the work, undoing the work, performing the work, undoing the work. I believe in this case, and is actually reflected in the way they chose the variable namings. The reason you can't do that is because it breaks it up into two pieces. So you actually need to do, there's a dependency here. So for instance, v1, in this case, the second piece, actually depends upon the value of v0. So this is where you kind of mix, you mix the, basically you're encrypting one half of, or I should say you're encrypting the second half of the data set with the, part of the first half. So this requires v1 to be unencrypted when it's doing when it's encrypting v0, and then v1 requires v0 to be encrypted, so to speak, when it's doing the, when it's encrypting v1, and then it returns both of those pieces. So there's a data dependency here, which means that when they are doing the reverse operation or the decryption operation, they actually need to also make sure that they maintain the right state over which one's like encrypted versus decrypted when they're working backwards. So in this case, you can't flip these two lines around and perform the encryption operation again. You actually have to basically, go through steps 3 through 1 for the decryption. So that's how they have it implemented here. So it's still, so basically decrypt doesn't equal encrypt, and they actually have it separated into two things. But one key thing that is noticeable here is that if I look at this line right here, this line is identical to this one, and this line is more or less, I won't say exactly, but is more or less identical to this one. The only big difference is the fact that the operation here uses a subtraction instead of an addition. So when they're doing the assignment, the last step of that, if you were to look at it from like an algebraic perspective, you end up performing this work first. Basically you end up performing the work inside the innermost parentheses before you work your way out to the outermost parentheses. So this line really performs everything that's on the right hand of the equal sign, and then it performs a subtraction of that data from the v1. So this is the same as doing this, I believe, right? So it's just kind of a shorthand for that. So the reason I point that out is just to kind of illustrate that the only difference here is that last mathematical operation that is an addition is actually replaced with a subtraction. So same is true with this line, and the same is true with this line. This line's really easy, but every one of these lines isn't able to be expressed as one single instruction, right? Based upon the previous classes that we had, what the compiler is going to do is it's actually going to turn this line into many instructions, into a really long list of instructions, which means that when it turns this line into a list of instructions and this line into a list of instructions, it actually starts to get to be a sequence of steps that look largely similar to one another except for the final step. So, so based upon that analysis of the code, what I ended up deciding to do was kind of do what I felt would be like the more straightforward thing of trying to change this algorithm slightly, which was let me take each one of these values that used to be inlined on a single line, so each one of these parameters here, and let me break them out into their own operations, and then just perform the XOR, the three-way XOR operation, as a separate step of its own. So basically, let me explode this single line operation into its literal, 4 steps, which is these right here. So I'm going to break it up into its 4 steps and manually tell the, in this case, manually tell the processor which sequence of steps to order. And I did the same thing here, and then I did the same thing down below in the subtraction or the decrypt routine. So that's kind of the tiny encryption algorithm that I'm working with right now, and as you can see, it fits nicely on kind of one big screen. So it's actually a really good one for our analysis. But notice that the key thing here is that I'm breaking up that really complex operation into more simple pieces. I'm sort of doing the compiler's work for it here, because at the end of the day, both of these are actually going to get broken up into a sequence of very simple micro operations. So I'm kind of doing the compiler's work here for it. So the other algorithm is a lot simpler, and this is one that I'd call more of a perfectly symmetric algorithm. So this one, you are literally able to give the plain text to this with a key, and then it will give you the ciphertext. And then if you run it back through the encryption routine again, it'll give you the plain text. So if you keep calling it, you'll just keep cycling back and forth between the same ciphertext and plain text. So what I did here, let me see, what did I do here? Yeah, what I ended up doing here was they actually have a step up here that ends up adding this, and I think I actually need to do this. I was actually going to do that. I think I can do it that way. Yeah, there we go. So we'll see if that ends up modifying the operation again. So I kind of do the opposite of what I did earlier. So, which is in this case, it's been exploded, and I actually try to compact it down and see if the code looks at all different. So we'll look at this one again in a little bit. It looks like it's actually roughly the same. So anyway, yeah. So for Yarra, and I'm not going to do the initial rule construction in front of you because that would take a really long amount of time. But I did do this ahead of time, so let me. I think I might actually already have this. Come on. Here we go. So I actually have the code right here in a big Yarra signature, and I'll make it a little bit more readable, like this. There we go. Let me expand this a little bit so you can see all of it. So this one is basically is a really long Yarra signature. If you recall, and I'm going to go and bring up the code again kind of here as an example. If you recall, when we were discussing how the program, or I should say how the compiler breaks up the program into functional pieces, it ends up trying to look for branching instructions, right? So it's going to identify this content right here as kind of like one block or one partition of information, one functional unit, basically. It's going to also identify, this is where it kind of gets interesting, it typically identifies this code right here as another one. So the interesting thing about for statements is that when the compiler breaks them up, this piece where the arrow is on the I equals 0 here, that piece ends up actually being considered part of the code above it, and then it ends up breaking up the function this way. So these three lines, and then the test and the increment, so all the code that's supposed to run on every single loop iteration actually becomes its own block. And then finally, this code down here, the final assignments that try to do the return by pointer, those things end up getting performed as a third block. So this code really breaks down into 3 blocks, right? So when I'm analyzing code, this is where knowing how the compiler is going to break it up into pieces really benefits me. Because if I go up here and say, the author of a tool that may implement this algorithm decided that in addition to these things that it's doing during the setup, they also wanted to have it do, I'm just going to put like junk in here, right? But they also wanted to have it do like all these other, pretend that those are a bunch of C operations or something. So think from the perspective of somebody who's looking for a, looking for an encryption algorithm, they end up usually finding code online, just like I did. And they may take it and stitch it into their program, but they may also want to add some of their own criteria to it. For instance, in this case, they may modify this function to use like a hard-coded key or something like that, versus a one that's passed through the variables. So they may change some of the code in this block to try and match, the context of their program, something like that. So the interesting thing about that is that even though that block gets modified by those changes, by those local kind of modifications, the code inside this loop ends up staying as its, as its own cohesive, concise block. Likewise, they may end up choosing to do something different here after they get the ciphertext out. So they may choose to start implementing some internet send routine or something here to try and send the data out over the network connection, which then, of course, would naturally look different than the 2 operations that they did here, which is literally just assigning stuff to a variable. Or I should say, assigning stuff to pointer or to cells within an array. So, what I like to do after I recognize this is I'm not going to be able to write a Yarra signature that looks for the C code, obviously, because all the programs I'm trying to look for are going to be compiled. So what I'll often do is I will compile it, or if I only have the compiled version of it, like if I don't have a copy of the source code, I can usually disassemble it, right? Again, this is where having a disassembler comes in very handy, because even if I had the compiled code for this and I tried to reverse it back to C code, other than helping me understand the logical flow of the program, which was definitely very helpful, having the C code doesn't help me write, say, file-based detection for it. So that's where I need to actually work with the assembly language and somewhat understand what's going on there. So I'm going to, actually I think I might already have this one open. Yeah. Oh, I have the tray for open. So let me do this. So I'm going to look at the #1 version, right? And we will look at the 64 and the 32-bit version side by side. And I'm actually going to do it this way. So give me 1 second to remember. And then I need to v-split. So for those of you who use Vim somewhat frequently, there's a split and a v-split that allows you to load a file and split the window. So I'm going to use that here so that you can see both of these things side by side. Here we go. Okay, that comes out pretty nice on the projector. So what we end up having here, this one's actually kind of neat how these two break down. So I have the 32-bit on the left-hand side, and then I have the 64-bit on the right-hand side. So one thing you'll notice is that I think these lines of code don't exactly occur too much, or I should specifically say these lines of code right here don't actually occur in the 64-bit side. This is, again, at the beginning of the function. And that's one of the interesting oddities that's different in the 32 versus 64-bit API. So things like that are things that you have to keep in mind, is that what's happening here is that calling a function, handling a function that has arguments, is a operation that's actually done differently in the 32-bit libraries of Linux than it is in the 64-bit libraries. So in addition to having slightly different operations and instructions, you also have sometimes a little bit different convention for what they call, or a little bit different implementation of what they call a calling convention. And so that's what it's doing up there. So let me go down here, and what I'm going to do is I'm just going to try and find out where these two things line up. And the best way to do it would probably be to look for this right here, right? Because this data right here ends up being that constant. So if I was to go back to, give me a second. I'm going to go and bring up the C code really quick. So, right here. I'm going to go and bring this up, and I should be able to keep it up. So this value right here is a very good thing to key in on, as well as the things above it. So you got this one right here, and then you got the other variant of it over here. So these two are actually pretty close in order to one another. And you'll notice that the other thing that it ends up having is that it has all of this set up right here. So all these move operations occur underneath that. And then we actually have almost the same, very similar sequence over here. In fact, if you look here underneath it, you end up having almost this with a different kind of prefix in front of it, 48. You end up having this same instruction. You end up having this same instruction. You end up having almost this same instruction, except it's kind of like the different mapping from, that was done on this line right here. So you start to pick out like certain patterns that are occurring over this. And kind of why am I looking at this? Well, let me go back to that Yarra rule that I had written, which is right here. So what I did here to build this detection rule is I literally went through all these bytes that were between right here. So I looked for this jump, which that jump is the initial call to go to the bottom of the for loop where the test is performed. Because as I had mentioned in the C code, this stuff right here ends up being all one block, right? The way that the processor, I've noticed, seems to construct this is it writes it basically takes all this code, and then it puts this line underneath it, and then it puts this line underneath that, and then it tests. So this ends up, the one I've got highlighted now, ends up being the final instruction in the loop, or the final lines of the loop. And then if that ends up succeeding, then it jumps back up to the top. So the way that the assembly language ends up getting written is that this actually jumps to the location where that test is performed. And then when that test succeeds, it actually jumps back up here to line, in this case, 5B. So we'll remember that because I'm going to go, and I'll leave this highlighted. I'm going to actually go down here so I can show you all. This is basically the code that's inside of that for loop. So the code that keeps cycling. So right now, if you look at what what's that?
So that's the for.
Yeah, that's the stuff that's inside of the for loop.
Yeah.
So what I've got highlighted right now in gray is all the code, all the assembly language representing the code that's inside of that for loop, and then everything that's left in white is actually the code outside the for loop. So this is me basically doing the assembly language review to separate those two or those three blocks from each other, right? So I can do the same over here, or on the right-hand side. So, but the addresses are going to be different. So what I can do is I can look for the jump instruction, which is right here, and then go to the line below it, which is 5D. So it's actually 1 byte offset. And then I can see that it basically jumps back to 5D. So this is the same thing. And I'll also say that the code that you're looking at right now is the code that I use to generate the Yarra rule that I have in another one of these windows. There we go. So I have this code right here. Basically lines up with this. And I'll try and see if I can get it on the screen as much as possible, but you can see that this code right here, the 8B45EC, actually lines up with this perfectly. So that's pretty insightful. So what can I do with this? So what I did was I wrote a very static, very specific signature that was looking for that implementation. What I can do with this now is, there we go, okay, is I can now use the Yarra pattern matcher to basically to try and match or try and search all the files that I have in this folder to see if any of them have this pattern. So again, remember that, and I'll just do this to show you. Remember, I've got basically 4 implementations of tiny encryption algorithm. So I've got the different modifications that I made, and then I also have 4 different versions of that trafer algorithm, which I think are going to end up being the same implementation in the end. But we can modify if we have time to get to that. I can modify the code and show you how that looks. So what I can do is, following the instructions that are up here on on Yarra, is I can basically bring in that Yarra rule, which is t.yar, and then I'm actually just going to run it recursively. Yeah, whoops, against everything in the folder. And so now what you can see is that I get a nice match on both of these. So if I had written the code, this is one of the first kind of, I've already done one of the first steps to making a decent signature, which is breaking the program up into those different functional blocks. Because if you recall, when we were looking at the disassembly here, there was all this code up here, basically between where I initialized that really long constant, the one that's like at 9E3779B9. So that line here, there's a bunch of code between there and when the loop starts that actually compiled into different instructions because of some implementation or architectural differences between the two processor versions or processor variants. So like the great example is this one right here. It looks like, for whatever reason, when these ended up getting compiled, and part of it's just because of the data size, that this instruction, which ends up being move whatever is located at 64 bytes, which is the hexadecimal conversion for 40 hex. Move whatever 64-bit value was 64 bytes before the pointer inside of the RBP register, read that data out of memory, and then write it into the RAX register. So in this case, this one's doing the same thing, but it ends up saying that it wants me to give it whatever happens to be 12 bytes ahead of the EBP pointer, which is the 32-bit version of that, and move it into EAX. So that's why this value here changes. So this value ends up being 12, and then this value ends up being negative 64, or 64 minus, right? So it ends up being 40 hex minus, or I should say 0 minus 40 hex, which ends up coming out to C0. So that explains why these are different, which that's already a variation that's introduced just by me choosing to compile the same program as 64-bit or 32-bit. And then on top of that, for whatever reason, on the right-hand side, on the 64-bit side, it put an extra byte there, which is a prefix byte, I believe, to make absolutely certain that the operation is performed using 64-bit values instead of 32-bit values, or maybe 32-bit values. Let me see what the C code actually is, because I think the second thing I said is correct. Yeah, so if you recall here, I'm forcing it to use 32-bit values. So what is happening here? What's happening here with this 48-byte is it's trying to make sure that it's actually doing a 32-bit operation. So my apologies. Even though this is a pointer that's an address value that's 64 bits, it's actually only moving 32 bits out of it, and it's told to do that by putting this prefix in front of it. If that prefix wasn't there, so if that was just a 3-byte instruction, then this would be executed as a 64-bit read. So this is where it's always handy to have the assembly language manual right next to you when you're trying to read these things. So that oddity is introduced because I forced the data type that was being used in the program to be 32-bit. So those are the types of things that we'd have to take into consideration when we're writing signatures for this type of thing. So yeah, so the other thing that I can do with Yarra is so I already did the test on it, right? Or I should say I already did the check on it to see if this signature actually detected them, but I would really like to know what was detected within the signature, or I should say what signature, or I should say where the pattern match was actually performed. And so in this case, I'll notice that I have one location in both of them, which isn't too surprising, seeing as how I literally grabbed bytes from one of them, basically that excerpt that I highlighted for you earlier in the disassembly. I grabbed those bytes, and then I literally pasted them into a Yarra signature to generate this for me. So it's not surprising that I only have one match. But if you recall, I actually have two functions in here that are very similar. So these functions largely have a lot of the same code in them. It just ends up being in different order. So one thing I might want to try and do, because I may run into a situation where maybe they only want to do the encryption one way. So maybe the encryption exists for them to obfuscate some of their network requests out, but they don't care if the responding data is encrypted. So maybe they only implement one of these algorithms in an attempt to to be clever or whatever. So what I might try and do is actually go back to the source code, and I might try and see if I can find that same loop in the decryption code as well. So remember, this is just the encrypt function. So I may want to go down here and see what does that look like in the decrypt function. So let me try and do the same thing, where this is where that jump is. So that's where I'm identifying the boundary between the for loop and the code before the for loop. And then the rest of the code ends up being right here. So what I'm going to do is just hold this up right here and see if there are any similarities, and I'll give you a quick caveat. I haven't actually inspected this ahead of time, so so this will be interesting. What I would expect to see, though, because we know that the operations are actually in reverse, is I would expect to see some of the code that's all the way down here actually being implemented, or I should say some of the code that's all the way down here actually being implemented closer to the top up here, and vice versa. Or in other words, let me go here and pull this out. So I would want to see at least some of this code implemented down here, right? So let's see if that theory proves out. How would I go about doing this? So I do know that this operation occurs a bunch. So I might actually be able to break up some of the work based upon occurrences of that operation. So this is the decrypt. So let me actually go up here to the first Xor operation, and let me see how it might line up with this one. So is the data, so yep, so maybe this move, and add, and move, and add, I want to see if maybe they are operating on the same set of data. So let's see. Actually, this is the one I want to look for. The other thing that we're doing in here, if that ends up not yielding any results, is that we have some very specific shifting operations as well that use constants, which means that whatever code that is compiled that actually performs this work is going to be implemented with these constants in it. So I can look at those things as a way to try and to basically try and hunt for the needle, so to speak. So let's see. Each one of these has a, has a 4 or a shift left by 4 and a shift right by 5. So maybe I should go back. I should go and look at that. So this one right here has a shift left by 4. I would expect that that is this code right here. So first V1 gets shifted left by 4, then there's an add, and then all of that ends up being saved somewhere. So this thing most likely is loading V1, so this is V1, into the register that it's, and then it's going to shift V1 by 4, and then it's going to move V1 over to EDX, and then it's going to move K0 maybe. Yeah, and then it's going to move K0 into here, into EAX. So it overwrites the old value EAX because we saved it temporarily here. So it's going to overwrite it with whatever K0 is. And then it's going to do this. So that ends up, so load effective address ends up being a address calculation instruction. So this is how you, excuse me, this is how you put an address in a register that's based upon a calculation. So in this case, I can't remember off the top of my head what all this is doing, but basically it's taking the pointer value that was put in EAX and it's adding, it's performing an operation where it adds, I think, EDX to it and multiplies by 1 or multiplies by EDX and moves it over by 1, something like that. Anyway, it's putting those into, it's putting the result of that into ECX. And then, can't remember, anyhow, this is a little bit more difficult than I expected it to be, but, you know, in a nutshell, without me diving too far into this, what we end up seeing here is the shift left by 4, the shift right by 5. So each of these is identified as being code that is performing this work right here. So maybe if I was to break up the operations that are occurring here into smaller pieces, I might actually be able to write something that can detect, say, both versions of this. So let me see, and let me just, okay, yeah. So here we go, the decrypt. So let me see if, yeah, so where am I at? Yeah. So what I'm looking at is basically trying to see if I can find this pattern in here. And I do end up finding it here. And so what I might want to do is I might want to just start breaking this up into smaller chunks like this. So I might end up grabbing this code here. I'll just do like this. So grab something like that, and I'll just say, I'm gonna not number, but ID these, and I'm gonna say and kind of what I'm demoing here is let's see. And what I'm going to do is break this up into maybe like 3 pieces, just to kind of show you an example of what I'm trying to do here, which is I'm going to try and break out these things, so the shifts and certain move operations like this. So what I did was I grabbed this one, and I grabbed this one, and you'll notice that this one here, the shift operation there, is actually the same as the one down here, and then the shift operation here is actually the same as the one over here. So what I can do is also say, well, I can start with this, and I can see where this gets us. So there we go. My apologies. So it needs to have individual separate variable names in order to be able to do this. So then what happens when I actually run this, might help if I show you the addresses that were present here, because I believe that these addresses are largely going to line up with this stuff. In this case, we end up having the decryption routine here for anything that's like past DE, which is the DE offset in the code. So anyway, yeah, that ends up being here. So what you can see, you know what, that's going to be difficult because I think that these are just the offsets from the beginning of the, no, they're not. Okay, the offsets from the beginning of the code. So I think there's actually some other data at the beginning here. But what I can do is I can look at it and I can say, okay, where was the first case where that matched? And so it's got one right here. And so I had a question actually, how to read the jump within that stuff. So the question was, how do I read this? So I'll just kind of run over this really quickly. There's a question about how to read the jump instruction that I've highlighted here. So really the way this is read is jump to this position. Number one, it's a relative to, a lot of times it's going to be relative to the current location. So it ends up being 62 plus 5b, or actually plus the next instruction, I think. So it ends up being 62 plus, well, yeah, 62 plus the next instruction, because current position is always the next instruction that I would read. So it's literally saying jump 62 bytes ahead of here. And then that puts it here. So whenever the disassembler runs, it actually auto evaluates where the absolute location is when it's presenting it to you. So what you're seeing here for the jump, and this is the case for a lot of the other instructions that do branching as well, is it auto evaluates what the position is. And then furthermore, the assembler, or the disassembler also does a lookup within the code if it can evaluate the symbol that's associated with that, and puts it in brackets here. So the stuff that you see in the angle brackets is actually not present in the code at all. That was inserted by the disassembler. So what you will notice is that this 8B45DC, so if I search for it here, 45DC, so if I search for it, it actually shows up in the encrypt function and the decrypt function. It shows up twice in each one of those. And then over here, it still shows up in the 32-bit version as well. So I've got it there. The interesting thing is that it doesn't show up in the modified version that I wrote. So for whatever reason, that's still not showing up in the modified version. But we have something now that's at least able to match both the encrypt and decrypt function just based upon the presence of certain features. So the other thing that I can add here is if I wanted to, because I know that these occur 2 times in each one of them, what I'm going to do is maybe say the number of occurrences is greater than 1 and see what that does. And so that's still matching it. If I was to do greater than 2, it would probably still match because it happens, because I have the encrypt and decrypt code in the same function. But if I was to go and maybe put it higher than that, let's see. I can't remember, 16 maybe. That's supposed to work. 1, 2, 3, 4, 5, 6. No. What's going on here? I might have to do this, or I might have found a bug, which is also entirely possible. Yeah. Oh. I forget that. The other thing that Yarra wants is it wants to force you to use all of the things that are, all the strings that are present in the file. So let me comment those out. I'm sorry, this is like, yeah. So now it's not matching on there. I know what the problem is. So let's just try doing this. I'm going to remove that code, the code, this first clause, because that's what's happening. So the interesting thing is that when I do write these signatures and part of it matches, it even dumps out the stuff that doesn't match, or doesn't match the entire criteria. So there we go, that's what I was looking for. So if it's greater than 4, which I think still fails, but what I'll do is I'll say if it's greater than 1, then match, right? So now I'm finding that code, and this is me writing that code and removing those, you know, the first signatures that I wrote. So let me, oops. So this is me running that code and removing the first signatures that I wrote. So so what I've done is I basically extracted a handful of features from here that allow me to have a broader signature that matches an implementation of the encryption and decryption routine. Naturally, this might be incomplete. I might actually have to go through and even maybe increase the, you know, increase the, basically the condition for every single one of these. But basically what happened is I'm saying that the number of occurrences of each one of these strings has to be greater than, in this case, 1, so it has to be 2 or greater in order for me to detect it, which might end up narrowing it down. I would probably also want to go through and try and see if I can find any other examples of this. So one thing I did, this kind of got me to thinking, like, okay, how can I try and do a better job of doing this without having to do it all by hand? So taking the disassembly that I have, and so this is kind of where, you know, so I have this disassembly. How this is really separated is this is actually separated into multiple different columns. So I have somebody asking some questions. I don't know entirely what the question is there, but you can follow. Yeah. So I don't know if you want to. You can. I'm not entirely certain if I can follow what question's being asked, but if you want to, you can try and email the specific question to me. I'm sorry, the speaker system in here doesn't work. So, yeah. So like, yeah, this right here. So this thing right here, this is one of the things that I was pointing out earlier, is just an oddity of the 32-bit Linux API. The entire reason it's doing this is mainly just to call the next instruction, which, like, I'll be honest, actually got disassembled here. So it would have actually probably, so this stuff right here is not anything that's reliable. This is just kind of like an implementation oddity of the, the 32-bit Linux API. So as you'll notice, this actually looks a lot more traditionally what you would be expecting to see. I'll be completely transparent. I do not know why they chose to do it this way. There's probably a very valid reason that relies upon calling convention or maybe stack smashing protection or something like that. I don't know what it is, but that's not something I would rely on. So generally speaking, when you call this function from within a program, you're going to be calling this address right here. So you'll be calling whatever that address evaluates to. And again, that's something that's going to change depending on where the linked library loads it in memory. Jump over here. What I'll do is, because this doesn't happen to be matching on the second implementation, what I'll do is I'll actually load up the second implementation. So T2, we'll just load up the 64-bit version again and take a look at that. So this is the 64-bit implementation of that TEA. It has the shift lefts in it, and I will just look by opcode like that. So you can see that C1E004, those, it's weird. Should just be in there. Did I load up the wrong one? Okay, well, apologies. Oh no, I know why it is. So one of these is in here. So C1E004 is in there, which is this one right here. C1E805. 8 homonyms. That one's in there. So then what's not in there is the 8B45DC. It's not in there for some reason. So if I was to go back here, so that narrows my problem space down a bit, right? So I'm trying to figure out, okay, I definitely have a match on these two with the variation, but for whatever reason, I don't have a match on this one. So I can go in here and I can try and find that one again, which is right here. And that ends up being this move instruction that seems to happen after, basically right before the shift left, right? So C1E004. So let me go and see. There we go. So this one ends up being 8B45D4, right? Yeah. So D4 instead of DC. So that's the missing piece here. So I can do 8B45D4, and that ends up occurring multiple times in here, although the DC version doesn't. So what I might end up doing to try, after I've analyzed this, is to try, okay, maybe I can just look for this, which allows me to put a wildcard on that particular byte. And now, if I run it, we'll do it like this without all the details first. You can see now I'm matching across all different sets of them. So after doing some more analysis on the two different variants that I had, and so you can kind of theorize in this case that maybe someone had released version 1 of their malware with a version 1 algorithm, and then they went in there after someone decided, like, oh, I'm going to try and write a tool that allows me to detect version 1 algorithm. Then they modified it slightly for whatever reason. Maybe to evade detection, maybe because they we're having some sort of compiler issue or something like that. So basically, I chase that by broadening my signature, making a little bit more, cast a little bit more of a wider net by adding a wildcard here. The other thing I can do is, if I want, is I can also just optionally use the OR operator to kind of get some of the same. Let's see, it's D4, right? Yeah, so you'll notice that not only did I get that one, but I also grabbed a bunch of other variations as well that are happening within there. So if I want to be a little bit more specific, I might do this. And so I'm still matching all of them, but now I'm only matching the ones that are like D4, and DC. So I'm matching exactly the ones that I'm looking for. So this type of approach, could be common to try and use. So then what I may want to do is, I believe I have some examples here. Let's see, there we go. So, no. I'm trying to look for, yeah, there we go. So I have like 10,000 malware samples there. So this is another set of samples that I actually pulled off of an open source repository, so none of them are like labeled or marked up or anything like that. But what I might want to do is try running it against that. I don't know what this is going to yield, but you can see that it's going through there and it's generating a whole bunch of data. So what I'm running into in this case is I'm running into a lot of code that ends up basically hitting on this, and it might be up to me to try and investigate those things to see how much overlap there is. If I, say, open up this file right here, and I decide to try and see what the contents of that file are by going to these addresses using like a disassembler like I was using, or using IDA free like I demoed in class before, or like Snowman or something like that, then I might be able to determine whether or not this code is actually part of a tiny encryption algorithm that's implemented in there. If I find that it's actually hitting on stuff that happens to be those operations, but not within a implementation of tiny encryption algorithm, then what my job ends up being is basically repeating some of the steps that I was doing, some of these extraction steps. So right now what I ended up doing was I extracted three things, basically three instructions that I found were kind of unique to this, this program. What I might want to do is start to work through like locality. So what do I mean by locality? Well, for instance, this 8B45DC actually happens right before the C1E004. And then this one happens right before this, right before this code. So what I might want to do is find out if that's something that I can, maybe convenient, or if that's something that I can rely upon. So I've got this thing right here before I shift right. I've got this one right here before I shift left. I've got a slightly different thing before I shift right. And then I have a slightly different thing before I shift left. So I can, for instance, take the additional steps to say that maybe I want those things to occur within a certain byte offset. So I'll go to like the Yarra documentation really quick. So because I can't memorize all of the different conditions that exist, right? So I can do this. Can't remember even if it's right here. Here we go. Have to remember. Maybe this is a, I think, there we go. First offset of each string. So this one ends up being a little bit more complicated. What I might end up doing is I might end up trying to fiddle with this one and see if I can get a version of it uploaded. But the other thing I can do too is I can try and say, what do we end up finding? That it ends up being this 8B45E0 or, and there's the E0 or DC, right? So maybe if I do this, and then there's a version of it over here too, F0. So maybe I look for that, and then what I end up doing is I look for try this. So let me try and look for both types of these. Right? And before I save it, oops. Before I save it, I'm actually going to, oh, oops. So then, let's see. So now, it might be a much better, if I do that right. So, let's see, did I do this? I did it in the wrong order, but that's fine. This code actually comes before that. And just to let you know, in case it wasn't clear, one of the nice things about the way that this is laid out is that white space is ignored as well. So you can add all sorts of white space in there if you want. So there's that. And then, so you'll notice that I'm not retrieving samples as quickly as I was before, which means my match rate is a lot lower with this new version. Now that I recognized that the occurrence of these two, the incidence of these two, so we'll just grab these two right here, right, are right next to each other all the time. So now, in addition to me looking for each one of those instructions, I'm also looking for their presence in being adjacent to one another. So they need to be adjacent to one another, and then that needs to happen any number of times. Now, what I might want to do is go through here and find out that, hey, every single match of this, I have at least 4 of them or 8 of them, right? And I can probably go over here to the algorithm version 2 to try and figure out how I capture the other 4 versions, because I will say that when we're looking through the code, they basically implement the same functionality, and so therefore the mathematical operations that occur in one, all of those have to occur some way in the other one, just the implementation is slightly different. And a lot of what we're seeing here is just where it chose to put things in memory and things like that. So where it chose to refer to things in memory, that it is storing stuff in memory. In other cases, it's keeping it in registers. So that's a big difference between these two implementations. I'm looking at, we'll say, our reference example here. So let's pretend that I went and spent the next 10 minutes, which I'm not going to do, going through the source code for T2. And then I figured out what the trick was to basically get it to match on the other 4 occurrences of these instruction pairs. Then I would be able to have an instruction that reliably retrieves those, basically all 8 of those features. So what I might want to do is then, narrow this set down, to anything over 7, right? So this ends up, of course, reducing my match rate here. But then, when I'm retrieving the test examples, I only get the ones here for which there are 8 or more occurrences of those instructions. So it's just kind of some examples of working through the code and trying to identify the different unique identifiers within it. The goal here is, of course, going to be to try and create a signature that can reliably identify this algorithm and not confuse it with another algorithm. And I could probably spend like 2 to 3 hours on it longer if I really wanted to, which is oftentimes the case. But that's kind of the code analysis piece for for doing Yarra matching. Is basically went in there, identified a function. In this case, it was an encryption function, so I identified some function that looks like it had some sort of utility. I started to extract data from it to create a matching signature. Managed to create one that at least matched the original code. And then it also just happened to match both the 32-bit recompiled version and the original 64-bit version, which was a nice feature. When I modified it a bit by trying to extract some of the operations and then just look for their occurrences, then I was able to create something that was able to match a re-implementation of the same algorithm, maybe a different author's implementation or something like that. So I was able to basically match 4 different implementations of it across 32 and 64-bit architectures. And then, after I felt I had something that was pretty broad in catching those two, then what I did was I ran it against a much broader test set that I have. Then it's my job to go in there and try and see if I'm see if I'm matching on tiny encryption algorithm, or if my match is too general and I need to start pulling in other features, like you'll see this stuff right here. So move add Xor, move add Xor, move add Xor, move add Xor. So that happens 4 times here, which means I've only really grabbed I've only grabbed the first 2, or I should say I've only grabbed these features right here around the shift. I haven't even grabbed the the move add Xor pieces, which is another pattern, an operation sequence that I've identified that itself might provide another set of signature, or another one of these things, another string pattern that then I can match against. And so then I could look for the occurrence of that one plus the one that I just built for you in front of, in class. So, and then I could say, anything that doesn't have both of those in it is not what I'm looking for. So, all right, I think there was like one more question. So there's a question about, okay, we have a little bit of time. So, well, I guess technically class is over. So you're free to go if you want. I was going to answer this one question before I shut stuff down, which was, can I explain how to read this line of code? So what's happening here, and it's important to remember that I grabbed disassembly, right? I grabbed code from the middle of the function, right? So there's actually stuff happening above here. One of the things that happened above here, and this was, this use was kind of described in the last slides, is that there's the base pointer, which basically keeps track of the location, or I should say, the position of the stack when this function started. So the position of the stack when this function started is actually where a lot of temporary data is stored. So the arguments sometimes are stored there. So local variables get stored there. if you have like string data and things like that, or array data that was from a previous function that may have been allocated on the heap, that's also there. So generally speaking, as this function executes, every time that you see it refer to some offset from the EBP register or the RBP register, depending on if it's 32 or 64-bit code, that is going to be referring to some sort of local variable. So some sort of local in-memory variable. So in this case, it's saying to find the local variable that's stored at 14 hex, which is going to be, or I should say negative 14 hex from the place where the stack began, which is going to be, what, negative 20? Yeah, so it'd be 20 bytes before that, and store that value in EAX. This one basically says to, after it does whatever it's doing here, after it adds it and then stores it, so it adds EAX to another value that's in memory located right next to where it just fetched it from. So these are actually two local variables that are right next to each other in memory. It took the first local variable and then it added it to the second local variable and then wrote that into memory. And so that's in memory there. And then it moves down here, and then it fetches the next local variable that's right after that. So you've actually got three local variables here right in a row. This is the third one. And I know that because this one's, actually there's 4 of them, I guess. Because this one's 14, so there's actually 18, and then a 1C, and then a 20. So takes this, puts it in EAX, and then it shifts EAX left by 4. So let me go here and just see if I can figure this one out. So most likely some, wait a minute, let me think, no, delta is stored at this position. So load delta into EAX, and then add delta to sum, and then store the result of that in sum, overwriting the original value of sum. So that's what's happening here. And then after that, there's, and I'm going to glean this just from what operation is happening here. So the shift, whatever it grabs and puts in EAX, it shifts it left by 4. Because there's only one thing that does that here, I'm able to, interpret that 20 hex, this thing at negative 20 hex position is V1. So move V1 into EAX, and then shift left EAX by 4. So, and then move it into EDX. So what it's doing is it's moving it out of EAX and it's moving into EDX. Mainly because there's some, I believe that there's some optimization in being able to load from memory into EAX. So that's why it moves it into EDX. So temporarily that gets stored in EDX. It might have been more efficient or something like that for the purpose of all of this. But what you'll end up seeing is that this next piece right here, so after it's moved it into EDX, it then executes a bunch of code that then adds EDX and EAX together. It basically does this thing right here. So remember, EDX is sum, and then whatever it fetched into EAX became V1, I think. Give me a second. Sorry. My apologies. It's actually, yeah, it's actually loading this one, and yeah, I'll have to I might actually have to run this code to actually figure out what exactly is going on here, or just sit and stare at it for longer. But for the most part, what's going here is, remember that in Unix world or the GNU compiler world, this is the, this is the from and then the destinations on the right-hand side. So every single one of these operations that's occurring is putting the result of the operation into whatever's on the right-hand side. So, I mean, I got down to about right here, and then I think the big question is kind of what is the nature of this right here. I would have expected that this would occur after both this v1 plus sum and this have been done. But I'll be honest, like, yeah, there's 4 XORs, so yeah. So yeah, so I have like the XOR call runs 4 times. I would have expected to see 2 additions that had to do with or whoops, sorry. I would have expected to see these 2 additions plus this addition up here, and that I'm not seeing it is a bit confusing. It's not a bug. It's most likely that the compiler was able to figure out that that it could add 2 things from this side. I think it was able to figure out that it could add 2 of the it could do the additions first and then do the XOR later, basically. So the addition is actually whatever associative, yeah. So basically, the compiler figured out an optimization to make that happen in less sequences of steps, and I just have to unwind that. So